In this video, we are going to talk about Jordan's lemma, which is going to help us do improper integrals that we might encounter in Fourier analysis. In particular, integrals of this nature, negative infinity to infinity f of x sine of ax dx, or negative infinity to infinity f of x cosine of ax dx. And you might recognize this from something you would see when you're trying to do Fourier analysis of a function f of x. This is our overview slide, which I'll spend about 5 minutes on before going over all of these topics in more detail and with more examples. First, we will quickly review improper integrals using residues. That was the topic of our previous video. And because it's closely related to improper integrals for Fourier analysis, we'll do a quick review. Next, we will look at Jordan's lemma. We are not going to prove Jordan's lemma, but we will be using it. And it says that suppose that we have a function f of z that is analytic at all points in the upper half plane y is greater than 0, and exterior to a circle z is equal to r naught. So here is my picture. Here is my real number line. Here is my circle of radius r naught, and we're saying that our function is analytic in the upper half plane and exterior to this circle. Then let's say we have CR, and that's a semicircle over here, where R is greater than R naught. So that's the circle we've drawn. Then for all points C on ZR, so when we integrate along this line, there's a positive constant M sub R such that M sub R is greater than any magnitude of f of z, or modulus f of z, and the limit as r approaches infinity of mr equals 0. In other words, this here will approach 0. Then for every constant a, the limit as r approaches 0 of the integral over cr of f of z e to the iaz will be equal to 0. So we'll look at this closer with an example. Next, we'll put together the ideas we have from doing improper integrals using residue along with Jordan's lemma in order to get a method for doing these improper integrals with the sines and cosines. And this will be our method here, and this will be our result. It's very similar to what we had for our improper integrals, and that our integral over a closed contour, where we can use the residue theorem, is going to be our integral along the real axis of our function f of z e to the iaz, plus the integral along an upper semicircle, c sub r. And according to Jordan's lemma, this goes to 0. If you do remember how we did improper integrals using residues, you will recognize this form. It's a very straightforward extension from that video. The difference is now we have the integral along the real axis f of z e to the iaz. But what we will do is if we have an integral of this form, in negative infinity to infinity f of x cosine of ax, we'll take the real part of the integral f of x e to the iax. And if our problem was to find the integral negative infinity to infinity f of x sine of x, we will take the imaginary part of negative infinity to infinity f of x e to the iax. And then we have this example here to illustrate our technique for integrating improper integrals from Fourier analysis. We'll do this example in detail in the main part of our video. And that concludes our overview. So let's go back and start with the review of improper integrals using residues. To use our technique of using residues to evaluate improper integrals, there are some conditions that our function f of x need to be met. First, f of x needs to be a rational function that can be written as p of x over q of x, where p and q are polynomials with real coefficients and no common factors. Second, we want the degree of q to be at least 2 greater than the degree of p. So what's in the denominator is of degree at least 2 greater than p. And last, q of z has no real zeros, but it has at least 1 zero above the real axis. So when we look at singularities of f of x, We don't have any zeros on the real number line where we're integrating, but we can have at least one zero above the real axis. Once we know f of x satisfies these conditions, we can use these steps to evaluate our integral. First, we replace f of x with f of z. So what that means is f of x is a function where the x is to suggest real values. So this is a real function with real variable inputs. But we can expand the definition of our f of x to include functions of other complex numbers as well, and then x just becomes another complex number where the the complex portion, is equal to 0. Then we can find all zeros of q of z, that is the singularities of f of z, and we are looking for the singularities above the real axis with zeros with positive imaginary parts. Then we set up a closed semicircular contour C, which is composed of two parts. It's composed of C1, the line from negative r to r on the real axis. So here we're integrating along the real axis, and also the semicircle C sub r, which goes up into the complex plane. The radius r for C sub r is large enough to encompass all the singularities, so those are the zeros of q of z. And then we can apply the residue theorem because now we have a closed contour. So the closed contour integral is equal to 2 pi I times the residue inside the contour, and that will be equal to the integral over the real axis, right? That's this first part of our closed contour. And because we're on the real axis, then we can change our f of z to f of x dx because we're only going to have real values of x when we're on the real axis, plus the part of the contour that's our semicircle C of r. And what we saw in our last video is when our f of x satisfies these conditions, then we can see that we can prove that this part here goes to 0. And actually, I'm not going to put that on there because I already have that note here. As r approaches infinity, this integral here approaches 0. And finally, for your reference here, this isn't so much about this technique, but we're going to be using this theorem to calculate the residues. So this is from the zeros and poles video that we had done previously. And the theorem says let p and q be analytic at a point z0. So the p and q are our function f of x equals p of x over q of x. So it's analytic at a point z0. If p of z0 is not equal to 0, but q of z0 is equal to 0, in other words, it's a singularity of our function, and q prime of z0 does not equal 0, then z0 is a simple pole of p of z over q of z, and the residue at z equals z0 of p of z over q of z is equal to p of z0 divided by q prime at z0. So we'll be using this quite a lot. And now to briefly go over this example, suppose we want to integrate from negative infinity to infinity the function 1 over x squared plus 1. We are first going to convert f of x with f of z. So we're going to have 1 over z squared plus 1 dz. We identify our p of z, that's our numerator, which is equal to 1, and our q of z, which is our denominator, z squared plus 1. We look to where q of z is equal to 0, and it has a 0 at z0 equals I above the real axis. It also has a 0, no, actually it doesn't. It has 1 0, which is z0 equals I. We see that it is above the real axis. Then we also see for our c sub r that any r greater than 1 is sufficient to contain our singularity, which is equal to I. Now we set up our closed contour integral. Again, the closed contour consists of the real number line from negative r to r, and then our semicircle of radius r. So our closed contour integral is equal to the integral from negative r to r. Remember, this is on the real number line, plus our integral over the semicircle. Looking at this, because we are on the real number line, we see that all the values that get plugged in for our variable are going to be real numbers. So we're going to substitute x again to emphasize that now we're on the real number line. So we're going from negative r to r, 1 over x squared plus 1 dx, plus our closed contour integral. Now we're in the complex plane, so we need to use z, 1 over z squared plus 1 dz. We can use the Cauchy residue theorem to evaluate this integral over the closed contour, the entire closed contour C, and we'll say that's equal to 2 pi I times the residue of the singularities inside. And we calculate the residue using this theorem here, and we get the residue is equal to 1 over 2I, which then this closed contour integral simplifies to pi, which means now that this integral here along the real number line, when we take the limit as r approaches infinity, negative r to r, 1 over x squared plus 1 dx, is equal to this pi, which is for our closed contour integral, minus the c sub r integral. So it's going to be pi minus, as r approaches infinity, c sub r 1 over z squared dz. But as we said, this will approach 0 as r approaches infinity because we checked that our function satisfies these conditions, which means that our improper integral of 1 over x squared plus 1 is equal to pi minus 0, which is equal to pi. So that's our quick overview or review of improper integrals using residues. If you need more, that was our previous video. Now, the goal of this video is to extend this technique of improper integrals using residues to integrals that look like this: integral of f of x times sine of ax dx, or integral of f of x times cosine of ax dx. You can see the technique is really very similar if you compare the steps to the steps we did for improper integrals using residue. The big addition we need is Jordan's lemma, which will help us show or prove that this integral over the semicircle, the upper semicircle, approaches 0, which means the next thing to look at will be Jordan's lemma. Here's Jordan's lemma, and again, we're not going to prove it, we're just going to be using it. So we have a function f of z that is analytic at all points in the upper half plane that are exterior to a circle. Modulus z is equal to r naught. So here is our picture. This is our x-axis, our y-axis is over here. We're in the upper half plane where y is greater than 0, and we're exterior to this circle. Actually, this is a full circle of radius r naught. And we want y to be analytic all through the upper half plane exterior to this circle. Then we're going to have c sub r, which is going to be a semicircle. We parameterize it as z equals r e to the I theta. So r is our radius, which is greater than r naught. And then theta goes between 0 and pi, not 2 pi because we don't want to go all the way around, just half a circle, 0 to pi. So this is our c sub r. Then for all points z on c sub r, there's a positive constant m sub r. So this capital M suggests that it's a maximum. So it's a maximum at this radius such that m sub r is greater than all the f of z's that are on this c sub r. Then the second thing is the limit as r approaches infinity of m sub r is equal to 0. So the maximum value of the functions will then be bounded by this maximum which approaches 0 as r goes to infinity. Then what we conclude is for every positive constant a, the limit as r approaches infinity of c sub r of f of z times e to the iaz is equal to 0. So let's look and see how we're going to use this. But again, the idea is that the integration over this curve of f of z e to the iaz will equal to 0. And just for reference, on our overview slide, Jordan's lemma is right here under our improper integrals, and Jordan's lemma will show up on this step of our procedure to do these improper integrals from Fourier analysis. But I do have one more thing to discuss before we discuss this procedure here. And that is, we're looking at integrals of this form, from negative infinity to infinity, f of x times sine of ax, or the integral, the improper integral, from negative infinity to infinity, f of x times cosine ax. And what we are going to do is we are going to consider the integral and actually I should have put limit as r approaches infinity, the integral from negative r to r, f of x e to the I ax. By Euler's theorem, this e to the I ax can be written as cosine ax plus I sine ax, which means this integral can be written the integral from negative r to r, f of x cosine ax dx, plus I, we can factor out the I, integral from negative r to r, f of x sine ax dx. So that means if our problem is, let's do this one first, is the integral, this improper integral of f of x cosine of ax, then we can take the real part of the integral of negative infinity to infinity f of x e to the I ax dx, because the real part is exactly the integral of f of x cosine ax. Similarly, if the problem we're trying to solve is this integral here, this improper integral, which I rewritten here, negative infinity to infinity f of x sine of x dx, then we can take the imaginary part of the integral of f of x e to the I ax, because over here, the imaginary part is exactly the integral f of x sine ax. So what we just discussed is over here. This is point number 5, or step number 5 on our overview slide. So if we wanted the integral f of x cosine ax, we're going to take the real part of this f of x e to the I ax. And if the integral is f of x sine of ax, we're going to take the imaginary part of our integral of f of x e to the I ax. But let's look at all the little parts we've discussed so far. So far what we've looked at is we reviewed the residue theorem to compute an improper integral, and these were the conditions that had to be met, that f of x was a rational function, f of x is equal to p of x over q of x, p and q are polynomials with real coefficients, no common factors, degree of q is at least 2 greater than the degree of p, and finally q of z has no real zeros but at least 1 zero above the real axis. And then we use these steps to evaluate the improper integral. First we replaced f of x with f of z. Then we found all the zeros, q of z, that is the singularities of f of x, and we identified which ones were above the real axis, that is all the zeros with positive imaginary parts. We set up a closed semicircular contour C to integrate, and C was composed of part of the real line and then a semicircle above the real axis. And then we applied the residue theorem. So we said the integral over the closed curve is equal to 2 pi I times the residue, which is equal to the part of the integral over the real axis plus the part of the integral that's the semicircle. The next thing we looked at was Jordan's lemma that said if f of z is analytic at all points in the upper half plane that are exterior to a circle, in other words, this yellow portion. And if c sub r denotes a semicircle where r is greater than r naught, then for all points on c sub r, there's a positive constant m sub r such that m sub r is greater than all the modulus of f of z, and the limit as r approaches 0 of m sub r is equal to 0, then we can know for every positive constant a, which is over here on our exponent of e, for every constant a, the limit as r approaches infinity of c sub r, this upper semicircle, of f of z times e to the az dz is equal to 0. Now we're ready to come up with our procedure for improper integrals from Fourier analysis, that is improper integrals where we have f of x times sine of ax, or improper integral with f of x times cosine ax. And you want to compare this procedure to what we had for improper integrals because it is very closely related. First, we're going to replace f of x by f of z, and again, that's exactly the same thing we do over here for just general improper integrals. Second, we're going to ensure that certain conditions are met, and the conditions are very similar. F of z is rational, in other words, f of z is equal to p of z over q of z. 2, p and q are polynomials with real coefficients, no common factors. This other one here, q of z has no real zeros, but at least 1 above the real axis. So that's all mirroring what we did before for improper integrals. Here we can say that the degree of q just needs to be greater than degree of p. We don't need this 2 or greater. But you can see how similar. The next thing is we're going to replace sine of ax, or cosine of ax in this case, with e to the I az, and convert our integral then to the integral over the closed curve integral, f of z times e to the I az, is equal to the integral over the line, this real line from negative r to r, f of z e to the I az, plus the integral over this top semicircle, c sub r, f of z e to the I az. But we see that this here, this integral over the closed, or I'm sorry, not the closed curve, but the semicircle fits the Jordan lemma. We're integrating along this upper half circle, and we're integrating a function f of z e to the I az. So this, according to Jordan, will go to 0. And we're left with here, our closed curve integral, again, is going to be our, where we apply our residue theorem. And this here, we're going to replace z with x because we're integrating along the real axis since we're on the real axis. So we won't have any complex variables as we integrate along the x-axis. We'll only have real variables. We let r approach infinity, and then finally our final step, this is the last point we talked about. So if we have sine times our f of x, then we take the imaginary part of our integral from f of x e to the I ax. If we have this form of our Fourier analysis where we have f of x times cosine, then we take the real part of f of x times e to the I ax. And this is where we are. On our overview slide, we reviewed our improper integrals with residue, we had Jordan's lemma, and now we have this procedure here for doing our integrals from Fourier analysis. So we're ready to do an example. And the first example we'll do is the one on our overview slide. I'm going to clear out this review of improper integrals and Jordan's lemma. Jordan's lemma I kind of denoted where we're using it, but I'm going to keep this for our reference, and I'm going to clear this other stuff out so we have a little more room. Okay, so here's our procedure. Here's our example. The integral from negative infinity to infinity, cosine of 3x divided by x squared plus 1 dx. And notice again, our variable here is x. So this is the type of integral you might have seen in first year calculus. It involves real variables, real functions. And the first thing we're going to do is to replace f of x by f of z and then identify our p of z and q of z. So here, f of x, and if you look at this, this is f of x times sine of ax, or f of x times cosine of ax. So our cosine here doesn't count as part of our f of x. Our f of x is 1 over x squared plus 1, and when we convert it to f of z, that's going to be f of z is equal to 1 over z squared plus 1 squared. Again, the form of this, the f of x, it's what's multiplied by sine of ax, or what's multiplied by cosine of ax. So what's multiplied by cosine of 3x here is 1 over x squared plus 1. Then our p of z is going to be the numerator, which is 1, and q of z is the denominator, which is z squared plus 1 squared, and I'm going to factor this out as z minus I squared and z plus I squared, set it equal to 0 so we can find our roots or find our zeros, and it has roots at z equals plus or minus I, but only z equals I is above the real axis. And I kind of skipped a step. I went straight to looking at the zeros, but also we should note that p and q have real coefficients, right? And they have no common factors, okay? And we also see the degree of q is greater than, in this case it's z to the fourth, it's greater than the degree of p of z, which is the degree is 0. So our conditions are met. So now we want to replace sine of ax or cosine of ax with e to the I az and convert our integral. So that's our next. So here I'm going to replace in my original integral my sine or cosine with e to the I az. In this case, a is equal to 3. So I have 1 over z squared plus 1 squared e to the I 3z dz. I'm going to move this over so that I can make room for this, converting this integral. So here we have our integral along the real number line, but now we want to write out this integral of our whole closed curve. So this integral here corresponds to this part of this equation, right? It's the same thing. Oh, except instead of negative infinity to infinity, I put the limit as r approaches infinity, integral negative r to r. But otherwise, it's the 1 over z squared plus 1 squared e to the I3z dz. And this is going to be part of our bigger integral, which is over our entire closed curve. So our entire closed curve, which we're going to call C, of 1 over z squared plus 1 squared e to the I3z, is equal to the integral over the line portion plus the integral over c sub r, this half semicircle over here. So limit as r approaches infinity of c sub r 1 over z squared, 1 over z squared plus 1 squared e to the I3z dz. And now you can see our notes will tell us that this part here, by Jordan's theorem, goes to 0. This part here is along the real axis, and we have that noted. And this part here, we can use the residue theorem. So let's go ahead and use the residue theorem as our next step. For this, we are going to use our residue at poles theorem because we have a pole here of order 2. Actually, yes, a pole at z equals plus and minus I, both of them of order 2. So we have an isolated singular point z naught of a function. F is a pole of order 2 in this case. If and only if f of z can be written in the form f of z is equal to phi of z over z minus z naught, in this case to the 2, where phi of z is analytic and non-zero at z naught, then the residue then of z equals z naught of f of z is equal to the m minus 1 derivative of phi at z naught divided by m minus 1. So let's take a look in terms of this here that we're applying the residue theorem. In this case, we're looking at the residue as z equals I. We're not looking at z equals minus I, since minus I is over here. It's not in our curve. And for our Cauchy residue theorem, we're only concerned about the singularities contained inside our curve. So we're looking at the residue, z equals I, and then from our function f of z, we need to factor out our z minus z naught being our pole, or our singularity, raised to, in this case, our pole is of order 2, right? We're looking at, over here is of order 2. So we need to factor out the 1 over z squared plus 1 squared e to the I3z, which means our phi of z is equal to this e to the I3z over z plus I squared. And phi prime of z, if I take the derivative, I get this ugly expression here, 3i times z plus I squared e to the I3z minus 2 times e to the I3z times z plus I all over z plus I to the 4th. And I got this, this derivative by using the quotient rule for derivatives. Continuing on then using our formula, our first derivative evaluated at z naught again is our z equals I, over m minus 1, it's the second degree, so this is just 1 minus 1, which is 0 factorial, which is just 1. So phi prime at I, plugging in I into this expression, gives us this ugly expression, negative 12i e to the minus 3 minus 4i e to the minus 3 over 16, which is equal to 1 over I e to the 3rd. Which means now our integral here along our real axis, negative infinity to infinity of 1 over z squared e to the I3z is equal to, this part goes to 0, so it's equal to what we have in the residue theorem. The residue theorem says that this integral will equal to 2 pi I times the sum of our residues. There's only one residue, and it's 1 over I e to the 3rd, which is equal to 2 pi over e to the 3rd. And the last step then is, there are two things actually we're going to do at the same time. First of all, this, because it's along the real axis, we can substitute x in it to make it a real integral. Second, our original problem was for cosine, so we need to take, for cosine, where is this? for cosine, we're going to take the real part of our solution. So our solution here, actually this I cancels with this I, so the whole thing is real, right? The 2 pi over e to the third, that's all of this is real. That means that our integral from negative infinity to infinity cosine of x squared plus 1 squared dx is equal to the real part of 2 pi over e to the third, which is simply 2 pi over e to the third. So that's the conclusion, or this is the answer to our first example problem. Because that went so well, we'll do another one. So we have this improper integral from negative infinity to infinity x sine of x over x squared plus 2x plus 2 dx. And the first thing to do is to replace f of x by f of z and also define our p of z and q of z. And here I have my f of x. Remember, I guess I should also mention f of x, right? The sine of x is multiplied by f of x. So f of x is equal to x over x squared plus 2x plus 2, which makes our f of z equal to z over z squared plus 2z plus 2. Our p of z then, that's going to be our numerator is equal to z. Our q of z is equal to our denominator, z squared plus 2z plus 2. And I went ahead and factored it, so I see that there are zeros at z naught equal minus 1 plus or minus I, and only one of these, the minus 1 plus I, is above the x-axis. So I went ahead and I looked for my zeros, but I should also verify that p and q have real coefficients, and you see the coefficients are 1, 1, 2, and 2, so they're real coefficients. They have no common factors. You can't divide this by z, so they have no common factors. And the degree of q is which is 2, is greater than the degree of p, which is 1. So all of these conditions are satisfied. So the next step is to replace sine of ax or cosine of ax with e to the iaz, and then convert to this integral that's our closed curve contour. This is kind of two steps. So the first one, replace sine of ax or cosine of ax with e to the iaz. So coming over here to our original integral, I'm going to have the integral from negative infinity to infinity, z over z squared plus 2z plus 2. I replace this sign with e to the iz. And now I'm going to set up my closed curve contour. So I have my contour over the entire curve C, which is this real number line and the upper semicircle of z over z squared plus 2z plus 2 e to the iz dz. I'm going to use my residue theorem on this portion. And then I have that equal to the integral along the x-axis. That's the limit as r approaches infinity, negative r to r, z over z squared plus 2z plus 2 over times e to the iz dz. And again, this is along the real axis, plus the integral over my semicircle, c sub r, z over z squared plus 2z plus 2, e to the iz. And by Jordan's lemma, this goes to 0. I'm always going to be using that fact. So looking here along the real axis, all these z's can become x's. So if I want to know what this integral is equal to, I can use the residue to calculate this side of the equation. I'm going to start just by writing that over here. So my integral z over z squared plus 2z plus 2 times e to the iz is equal to then 2 pi I times the residue of this function, z over z squared plus 2z plus 2 e to the iz. I am going to use this same residues at Pohl's theorem. Isolated single point z naught of a function is a polar vorticity M if and only if f of z can be written in the form f of z is equal to phi of z, and then factoring out my poles where phi of z is analytic and non-zero at z naught, then the residue is equal to the m minus 1 derivative of phi evaluated at z naught, m minus 1 factorial. So my phi of z is equal to z e to the iz, and then in my denominator, it's I'm going to use how I factored it out, but I'm going to take out where I have my singularity above the x-axis, which is negative 1 plus I. So this is what's going to come out, and I'm left with the z minus 1 minus I over here. So then I can plug in phi of minus 1 plus I. That's my my singularity above the x-axis, and I get minus 1 plus I e to the minus I minus 1 all over 2I. You know, to make a little more space, I'm going to get rid of this residue theorem and move this up a little bit. That means my integral, my original problem, negative infinity to infinity, x sine of x over x squared plus 2x dx, is the imaginary part of this integral over here, which is the integral of negative r to r, z, in this case, by this time, my z is replaced with x over x squared plus 2x plus 2 e to the I x, which we just calculated using the residue theorem, is equal to, so I'm going to put my 2 pi I, my residue, which is negative 1 plus I times e to the minus I, and in this case, my e to the minus 1, I just put my e in the denominator, times 2I. So this 2 and this I cancel out, so we get the imaginary part, and I have my pi, I have my minus 1 plus I over e, and then my e to the minus I, using Euler's formula, becomes cosine of minus 1 plus I sine of minus 1. I multiply this out, and then when I take the imaginary part, I'm left with pi over e cosine minus 1 minus sine of minus 1. Since cosine is an even function, this is the same thing as cosine of 1. And since sine is an odd function, that's equal to sine of 1, but I have to put a negative sign. But with this negative sign, that gives me a positive. So this is the final answer, pi over e cosine of 1 plus sine of 1. To review what we have covered in this video, we looked at improper integrals of Fourier analysis and Jordan's lemma. The first thing we did is reviewed improper integrals using the residue, Cauchy's residue theorem. Next, we look at Jordan's lemma that said if we have a function f of z which is analytic at all points in the upper half of the plane that are exterior to a circle, modulus of z is equal to r. So in other words, our function is analytic in this yellow portion above the y greater than or equal to 0, and outside this circle of radius r naught. Then if c sub r denotes a semicircle where r is greater than r naught, so we have our semicircle, r is greater than r naught, then for all points z on CR, there's a positive constant m sub r, such that m sub r is the maximum or is greater than all modulus of f of z. And if we know the limit of r approaches infinity, mr equals 0, then for every positive constant a, the limit as r approaches infinity, c sub r, f of z, e to the I a z dz equals 0. So this is our final conclusion, which we will be using over here. We can now use Jordan's lemma to extend our technique of improper integrals using residues to improper integrals of a function f of x sine of ax, or an integral of f of x cosine of ax. These integrals are some that you see often when you have Fourier analysis. And this here is our procedure for doing these improper integrals. The first step is to replace f of x by f of z. The second is that we want to ensure these conditions are met, that f of z is rational. It's equal to p of z over q of z, where p and q are polynomials with real coefficients and no common factors. Next, we see that the degree of q is greater than the degree of p. And then last, we want q of z to have no real zeros, so none on the real number line on the x-axis, but at least one zero above the real axis. And remember, we don't want q of z to have any real zeros on the real axis because we are going to integrate along the real axis, and if there's a zero there, we'll have trouble. The next step is to replace sine of ax or cosine of ax with e to the IAZ. So now instead of this integral or this integral of f of x times sine of ax or f of x times cosine of ax, we're going to have the integral of f of x times e to the ix. And then if our original integral was for cosine, then we're going to take the real part of our f of x times e to the ix, and if our original problem integral was f of x times sine of x, then we're going to take the imaginary part over here of our integral f of x e to the iax. Our example is the integral from negative infinity to infinity cosine of 3x over x squared plus 1 squared. And we note that this function is a function with real variables x along the real number line with a real valued function. But the first thing we do is we take this function and we extend it to the complex plane, because certainly the real number line or our real numbers are a subset of our complex numbers. They're just the complex numbers with zero imaginary part. So we're going to extend our function to f of z equals 1 over z squared plus 1 squared. And so again, the z and the x, they have significance here. X is when we're considering specifically the real numbers, whereas f of z we're considering the complex numbers. The reason why we go into the complex plane, again, is so we can use our Cauchy residue theorem. So now we've done our first step, replace f of x by f of z. We're going to identify our p of z and q of z and make sure all these conditions are met. So our p of z, that's the numerator, which is equal to 1. Q of z is our denominator, which is z squared plus 1 squared, which is equal to z minus I squared, z plus I squared. We look for the zeros and see that there are two zeros, z equals plus or minus I, but there's only one above the real axis, that's z equals I. So we've confirmed that p and q are polynomials. We see they have real coefficients. The coefficients are 1 and 1, and no common factors. And we can see that they have no common factors. Well, I guess 1 is sort of, no, they have no common factors, so we're good. And then also q of z has no real zeros. In other words, it only has zeros that are imaginary, and 1 above the real axis, that's z equals I. And the degree of q is greater than the degree of p, because the degree is, well, actually it's 4 here, and here it's equal to 0. So we're good with all these conditions. Doing the next step, we're going to replace our sine of ax or cosine of ax with e to the iaz. So we're replacing this cosine of 3x with e to the I 3z. So our integral now is negative infinity to infinity, 1 over x squared plus 1 squared times e to the I 3z. And then we're going to convert to this integral our closed contour integral. So the integral over the entire closed curve of 1 over z squared plus 1 squared e to the I 3z, we can use the residue theorem on this, Cauchy's residue theorem, is equal to, so this entire integral, we can break it up into two parts. The integral along the real number line, so limit as r approaches infinity, negative r to r, 1 over z squared plus 1 squared e to the I 3z dz. And again, this is along the real axis, so later we can convert this to x's instead of z's, plus the limit over this semicircle, which is limit as r approaches infinity, c sub r 1 over z squared plus 1 e to the I 3z. And this is exactly the form of Jordan's lemma over here, right? We have an f of z times e to the iaz over a semicircle. So this is going to go to 0. So what we have left is this integral then, which we can say is along the real axis, is equal to, and we need to apply the residue theorem. So we have the poles at our residue theorem. I'm not going to go through this calculation, but we found that the residue is 1 over I e to the third, which means our integral here along the real axis, and now we're going to plug in x's. No, we didn't. Okay. Well, this integral then is equal to 2 pi I times our residue, which is equal to, which implies now, here, because the i's cancel, we're going to have the integral then of cosine x squared plus 1 squared is equal to the real part of 2 pi over e to the third, which is simply equal to, there's no imaginary part, the i's canceled, is equal to 2 pi over e to the third. And that's it for this video. Thank you for watching.